Lance, pleasure to meet you.
Pleasure to meet you too. Very happy to be here.
What are you all about?
What am
Introduce
I?
yourself.
Oh yeah. Well, my name is Lance. I'm doing my PhD with Karl Friston. My background is in mathematics. So I did pure mathematics for a while, and I started thinking about what I wanted to do with my life. It was all very abstract, and I was just really interested in the brain. Like a lot of people in my family have psychiatric diseases, so I guess that was a clear motivation. And I was also super interested in artificial intelligence. I started thinking about all of the technologies that would transform society. And I had this moment where, I had to make a decision. What am I going to spend my life doing? And obviously, I wanted to have an impact. And out of all emerging technologies, I mean, artificial intelligence seemed the thing that really got to me. And it seemed the thing that would have the most profound impact on society as a whole. So I decided to go in there, and I quickly realized that a lot of what people were doing at the time was not principled. It was mostly based on deep learning, and I was really disenchanted with this approach. I guess it was really like this pure mathematician's attitude to things, where you want to have proofs, you want to have theorems, you want to have guarantees, you want to really understand what the system's doing, and you want to, I wanted to understand what intelligence was all about. And deep learning, I mean, to some extent they can do smart things, but they really don't tell you anything about the nature of intelligence. Mm-hmm. So I decided to go into neuroscience as well for that other reason. And so I started hearing about the free energy principle. It was a friend at the time who told me about, there's this amazing paper about the free energy principle. Is it a unified brain theory? So I read that. I didn't understand it at all, but it just seemed really exciting. So I decided to, get into that space. I started working with Karl Friston. I did my thesis with him. And basically, I realized that the free energy principle had a lot of potential, or at least it seemed like it had, but there was no underlying mathematical theory supporting the principle. Mm-hmm. So it's like we make this claim that all intelligent agents minimize free energy, and they do that for perception, action, decision-making, and whatnot. But we claim that we have this principle, but we actually don't have, rock-solid reasons to believe that this is true. So basically, my thesis has been about laying out those mathematical foundations that would justify why the principle is right. And I'm super happy to say that now, or at least in a couple months, we will have papers out that will, show the rock-solid foundation that would be able to convince any mathematician or physicist that's interested in the subject of if you have a brain or if you have an intelligent agent that's out there, it has to comply with the free energy principle. This is just how things work, how physics work. And, this lays a rock-solid foundation for principled AI, I think, in the many years to come. I mean, maybe this is the end goal theory. We'll see.
Yeah, I mean, there's three interesting things to touch on there. I mean, we should discuss what you think intelligence is. But you were saying that we need a mathematical foundation for the why question and also for the necessity question. So why don't we start with that? So what work have you done to kind of demonstrate the why the free energy principle is true?
Well, so you have to start from the basics. And when I say basics, from basic physics, of what it is to be an agent, what it is to interact with the world. And I would say the fundamental tenet or the fundamental assumption that underlies the free energy principle is that any agent has a boundary with its environment and is going to exchange information through that boundary. And moreover, the boundary that you and I have with our environment is comprised of sensory states and active states. And so you have this kind of cybernetic loop, this flow of information for the environment influences your sensory states, your vision and whatnot. Sensory states influences the brain influences the active states. You're going to do movement, for example, and act on the environment. And so if you just start with those fundamental assumptions and you say, well, I mean, there is some dynamics. I mean, the world evolves, you as a person evolves, and there is this interaction. And you take this very general formulation of dynamics that underlies all of physics theories, which is based on stochastic differential equations.
Mm-hmm.
If you say that the world and the agent are governed by a stochastic differential equation, and this is in itself not really an assumption because statistical physics, quantum mechanics, they're all based on stochastic differential equations. If you just start with that, you just do a bunch of derivations and you can show that the internal states, the brain, minimize free energy. And in so doing, they infer what's going on in the environment based on the observations that you have. So it's basically just a theorem.
Okay, but if I understand correctly, you're saying given some assumptions, and there are quite a few assumptions, so the primacy of an agent and the this concept of a cybernetic agent loop where we pass information around in a multi-agent system. And then you're kind of saying, okay, well, we're using similar models to what we do in physics, so like stochastic differential equations, and we can then look at how the dynamics change over time, and things like the repartitioning of entropy and so on. And you're kind of saying, okay, well, so I'm looking at that process now, and based on that process in many different environments, that's answering the question of why the free energy principle is true.
Yeah, but you make it sound a lot more complicated than it is, okay. I think. So you're just saying there has to be a dynamic that governs the world, and we're just going to take the most general model of dynamic that exists, which is stochastic differential equations. This assumption is not an assumption because all of physics is based on stochastic differential equations. And so if we want to describe the world, if we want to have a theory of the brain, which is part of the physical world, then we should be starting with that. And then the other assumption is the notion of a boundary. Now, the boundary is allowed to interact freely with the environment and with the brain. But then you just say there is a part of the boundary that need not interact with the brain, like need not influence the brain directly. This would be the active states. And there is a part of the boundary that need not directly influence the external states, the environment, and those would be the sensory states. Mm-hmm. So you basically just have this boundary assumption, and then the free energy principle follows. And I would say all the rest is just like cosmetic stuff, but which is basically very natural when you're a physicist.
Interesting. I mean, a couple of things on there. I mean, first of all, I love the idea of there being a physics of intelligence. And that's because
it's awesome.
I philosophically believe that intelligence is a material, physical thing. I don't think it's like a purely abstract, virtual thing. So I'm on board with that. But I guess, would you accept that it might just be a lens? Like any other physical theory, it's like an intelligible abstract lens that seems to give a lot of predictive power, but might not represent the real thing.
Yeah, it's a very interesting you say that. So, I mean, for sure it is a lens because we're using the lens of physics and mathematics to express things. And so we're basically deriving equations. Now, but then again, the beauty of mathematics and physics is that you have equations that really represent, or that we believe really represent something that's out there. Now, I believe the free energy principle can be considerably refined. At the moment, for example, the fact that we have just very few assumptions on the theory means that the free energy principle just applies to stones. It applies to birds, it applies to any kinds of animals, it applies to cells and viruses. And it's cool. I mean, we get this really sparse and general description of what intelligence is. But then you can also argue, if this description of intelligence can be applied to stones, is that really so useful in and of itself? So it is useful because we can use these equations to create artificial intelligence. But as we move forward, we want to refine the free energy principle to have a description that applies exclusively to brains and not to other animals that we think are less intelligent. And as we move towards these more refined description, then we get more powerful algorithms that create more sophisticated forms of artificial intelligence.
Yeah, I mean, I think it is useful in so many ways because we anthropomorphize intelligence. So it's the least anthropomorphic definition of intelligence there is actually out of all of them, and I study all of them.
Mm-hmm.
And it also allows an externalist view of cognition, which I'm very big. Well, it's an integrated view, so you can have a combination of minds which have representations about the world around them, but also, like a kind of a distributed composition of minds that act as a single mind, depending on some abstract boundary.
Yeah.
And and also this material view of intelligence, which I think is very, very powerful. So I think it's very, very instructive to think about intelligence in this way. But of course, it's similar to how biologists think of intelligence. It's not something that really makes sense to a lot of people because you're just thinking about it almost as a form of dynamics in a physical system rather than something we would recognize.
Yeah, that's true. But I would say if you want to express intelligence in mathematics and physics, in the end, it will have to be dynamics because things happen in time. And as you're making decisions, you're doing perception, it's going to take time. The language of dynamics is what underlies all of our physical descriptions of things. And I would say, and you were saying how biologists think about intelligence, and it's maybe a less of a tangible understanding, and that's all right. But I would say like a lot of scientific progress is just like it paves the way for physical and mathematical theories at the end of the day once our comprehension has matured. At least that's my point of view. And what's really exciting with intelligence and neuroscience at this particular point in time is that we're starting to be able to have these physical and mathematical overarching theories for what the brain is doing. And there's still a lot of work to be done in terms of refining the free energy principle. Like I would say we are at the level of intelligence 1.0 in terms of the free energy principle. We have the first iterations of the free energy principle that are rock solid. All this description of intelligence and cognition that applies to a wide number of organisms, that's now rock solid. But now we need to refine and move to intelligence 2.0, 3.0, and so on. So it's going to take a long time. But this is, in my opinion, a very important moment in science in that we're starting to have physics and mathematics actually be able to describe the brain in a very profound way, even though it's still very coarse-grained, the description that we have in terms of the free energy principle. And now we can have physicists and mathematicians, really talk about the brain and collaborate with neuroscientists and work towards what could be, an ultimate theory of the brain that's specific to the brain, much like you have an ultimate theory of the movement of planets with general relativity and so on.
Yeah, this makes a lot of sense to me, and it's biologically plausible in a way that current neural networks are not.
Yeah.
And I was just saying earlier in one of my other interviews that there are some relations to artificial life, like cellular automata, but this is somewhere in the middle because we're explicitly modeling agents, and the agents have, selfhood, and they can model other agents, and they can have a lot of the kind of dynamics that you have in artificial life, but we can steer them. But steerability is this trajectory, on these different levels of implementation. So artificial life is not very steerable. The free energy principle is slightly more steerable, and neural networks is very steerable. And I think we're kind of going for this middle way where we are using active inference, and we might use some components of other models. So we might use, let's say, encoders, like transformers encoders, or we might endow certain cognitive primitives into the models. We were talking about cognitive primitives last night, and we're going to end up with some kind of hybrid which uses all of these different approaches we're talking about, and we think that something very intelligent could emerge from that, far beyond which is possible with neural networks.
Yeah, I mean, this is very interesting. So, I mean, you've highlighted kind of like three converging themes. I would say there's the free energy principle, which gives us a principle and some equations to implement to have intelligent behavior. Then the other one is core knowledge, like what is kind of your starting point or your prior understanding of the world that is potentially shared by, infants, and that leads to a more human-like form of intelligence and understanding. And then there's the third pillar, which is taking techniques from engineering and deep learning that are out there and that work very well for a number of things to scale up those models based on the free energy principle. And it's true that for the past few years, in our community, we see like closer and closer integration and convergence between free energy principle, active inference, principled algorithms that unfortunately at the moment do not scale as much as we would like them to. And then we take all of these techniques from AI, like deep learning, reinforcement learning, ways to scale those reinforcement learning algorithms, and we combine them together to have principled and scalable algorithms. Mm-hmm. I would say, though, this is very exciting, but I would say, though, this is just a stepping stone, because we haven't yet found proper principled ways to scale those active inference algorithms. And in my opinion, the key to do that, well, there's actually two keys. One is structured learning. So the thing that we are not currently able to do in active inference is to learn a model of the world in a scalable way. And by that, I mean, like, if you have a robot be in an environment that it has no idea about, like, how is the robot going to construct a model of that environment? The fact that I'm sitting on a chair and there's other chairs around me, and that if I, walk in a certain direction, I'll end up bumping into a chair and so on. This is something that infants do extremely well just by exploring their environment. And, learning by trial and error and constructing this like very rich model and detailed description of the world as time goes on. And this is something that we do not know how to do right now. So I would say this is like the major technological leap and conceptual, theoretical leap that we need to do in the next couple of years. So that's one thing, the structured learning. Mm-hmm. The other thing is the core knowledge. Yeah. So as we evolve and we want to build robots and AI systems that interact with us, we want them to share similar or ideally the same representations of the world and understanding of the world that we have. Yeah. So that's one thing. And the other thing is that if you want to do structured learning, you want to, create this model of the world. If you actually want to instantiate that mathematically or in code, it just turns out to be like a very hard optimization problem. Like, it's like, I'm in this room and there's all these possible models of the world that I could use to describe this room. 99.9999% of them are just going to be rubbish. They're not going to describe chairs. They're not going to describe ceiling and so on. They're not even going to correspond to any type of naturalistic environment. So you just want to exclude that and search that space of world models until you converge to a world model that actually does a good job of explaining your environment. This is an extremely hard optimization problem. And the reason why we're not able to do structured learning just yet, and it's not just us, but it's basically everybody in the machine learning community, and I would say like so many groups everywhere in so many different communities and converging to that ultimate problem of structured learning from many different directions. So we're not able to solve that optimization problem. And actually, I believe the key to solving that optimization problem and the structured learning problem at large is core knowledge. Yeah. Absolutely. So core knowledge is just like, so there's this great paper by Elizabeth Spelke on core knowledge, these six systems of core knowledge that we are born with. Yeah. So there's like innate core knowledge on objects, innate core knowledge on agents, basic mathematics. There's a bunch of them. Yeah. And so if we are able to reverse engineer that core knowledge, encode them as priors in the active inference models that we have, then this really constrains the space of generative models and world models that you would want to use to represent the world. Yeah. So all this core knowledge, I mean, it's amazing because it's like things that you don't even think about, like, for example, object permanence. Object permanence, like, of course objects are permanent and we never think about it because it's so obvious. But now if you're able to, take that thing and encode it as a prior or as a constraint on your search for world models, then it really decreases the complexity of the search problem. It really decreases the size of the space of world models that you want to search. I mean, and so I guess with that, this would be the way of solving structured learning in the long term.
I agree. It'll help a hell of a lot, and I love Spelke's paper. And manifestly, we know this is the way the human brain works. For example, with the grid and place cells, we have spatial priors, And even the concept of an agent is a spell key prior, and the agent is foundational to the free energy principle. So I mean that does give me pause and reason to think that it is a fundamental thing, and that's why it's in there. But as you know, there are an infinite number of structured representations, models for the environment that we're in, and many of them need to be significantly more nuanced than the spell key priors. So then, like, we've already had this tradition in machine learning with the bias variance trade-off of producing inductive priors that do things like symmetries and God knows what else, and receptive fields, for example. And Rich Sutton came along and he wrote this essay called The Bitter Lesson. And he basically said that, all you need is computation. Any attempt to imbue symmetries and priors and human knowledge into systems will inevitably fail. Well, reinforcement learning is not doing terribly well at the moment. Yeah. And you look at things like ChatGPT, because, in the olden days, we used to do expert systems and they were brittle. And then, we had the Rich Sutton phase of doing reinforcement learning, just from machine learning priors. And now we're kind of back to ChatGPT, where it's all human encoded knowledge again. So, like, where do you fall on that?
Well, it's really interesting. And I just want to, like, concur with, those. I mean, there's a lot of divisive opinions right now. And I was at this reinforcement learning and decision-making conference last year. And it was really interesting because this conference, so there was Richard Sutton. There are also core knowledge folks like Josh Tenenbaum, who, spend their life reverse engineering core knowledge. So there was all this crowd from DeepMind and all the like hardcore RL people like Andrew Barto, Richard Sutton. And then there were a bunch of neuroscientists, very famous ones, Josh Tenenbaum, Peter Dayan, and so on. And there were basically two different opinions, two different camps. There were the reinforcement learning people, and I think that was in particular like DeepMind. The DeepMind people really thought in this way of like, you just need compute power.
Yeah, and reward. Reward is enough.
Yeah, exactly. Yeah. The reward in it is enough, people. You just need compute power. And, if you have enough compute power, you can train your agent for God knows how long, and it will end up learning the core knowledge that it needs, I guess, to operate in its environment and much more. And then there are the other people like Josh Tenenbaum who want to create like human-like artificial intelligence and human-like sample efficiency. And they're very interested. I mean, they think core knowledge is the way to go. And I really agree with that. But I would think... actually, the reason why there is this divide is that the goals are different. People like Richard Sutton, they do not want to be constrained by human-like artificial intelligence and the representations that we have. They want to, just create intelligence and see what emerges. And for example, when we think about, the Go, AlphaGo and all of these like programs for playing Go and chess, they come up with like really new alien creative ways to solve Go and chess, ways that probably you could not have come up with if you had like human-like AI that had our core knowledge.
Could I touch on that though?
Yeah.
You're absolutely right. So that is the argument. So when you train, and the early versions of their Go system did train on human episodes, and that weirdly converged. It hit an upper limit of skill. So when they did the self-play, the skill ceiling was significantly higher, which was fascinating.
Yeah.
But it's not quite as simple as that, though, is it? So and by the way, it still converged, but much higher. But there was a kind of structure to it. So we all know that the skill space is exponentially large. Like all of the computation in the universe wouldn't let you saturate that space. So if you think about it, there's this very structured space that AlphaGo has learned. There's kind of manifold, and I call it the Swiss cheese problem, which is that there are all of these holes in the Swiss cheese. So like if you adversarially, like this has been discovered recently that humans can like make some weird moves. Even during the game, that move 47 on AlphaGo, it made a train of crazy moves. It was just suddenly playing like a child. It wasn't playing like a super intelligent machine anymore.
Oh, cool.
So it's a bit of an illusion. It's far more pointillistic than we think it is.
That's really interesting. I mean, the way I think about it, I always come back to like this intuition of like the no free lunch theorems.
Yeah, exactly.
And I feel that the more amount of core knowledge and priors that you're going to give your system, whatever that is, the faster you're going to learn, but the more constrained you're going to be in the solution that you end up with. And I would say the neuroscientists and cognitive scientists, they want to have this human core knowledge because they want to understand our brain. They're not so interested in artificial intelligence. They want to reproduce exactly what our brain is, and so they want to converge on the solution that us as humans have converged at in terms of intelligence. On the other hand, the people doing hardcore artificial intelligence, they don't care so much about the human brain, and they just want to see how intelligence can we really get. We have this enormous advantage of like, we're not constrained by the resources that our bodies have. We have immense amounts of computation. So let's just harness that, put less core knowledge, even maybe no core knowledge at all. And then we're going to, let the agent train for a very long time and converge into a much smarter agent. I would say the only drawback is once you have that type of agent that does not necessarily share our representations, then it becomes very hard to communicate.
That's very true. And I would also say like the benchmarks are completely broken. So I mean, recently there were examples of GPT-4 supposedly playing at an ELO of 1800. And that's just bullshit, right? Because you can't take, this is a problem all the time that people say, humans that can do A can do B. Therefore, if a transformer can do A, it should do B, which is like extrapolating on the human manifold of intelligence in the domain of machines. The same thing with benchmarks. You can't just take the benchmark of, the whole point of skill is you're talking about extrapolation between like other humans in the same population. So like talking about human ELOs in respect of GPT just doesn't really tell you anything. And even with the self-play thing, like, the only reason why those holes in the Swiss cheese were not found during self-play is because, like, for whatever reason, their self-play exploration policy wasn't exploring those parts of the search space. So that's the thing. I think people just don't understand just how ridiculous and brittle these benchmarks are. There are no systematic like evaluations of any of this stuff.
Yeah. I mean, it's like apples and oranges at the end of the day. Yeah, exactly. I think as long as you don't have human-like core knowledge, then you're comparing apples and oranges. And I think it just comes back to the fact that back in the day, I mean, beating the world champion at chess was considered a huge feat of artificial intelligence. Now, no one thinks about it because it's obvious that machines play better at chess than us, but we still think that machines are overall very dumb. And it just like, the fact is machines are just very good at doing things that we're not good at, and vice versa.
Yeah, was it Minsky? I can't remember who said, when we solved chess, then we would have solved artificial intelligence. But
yeah,
this is the amazing thing. There are all of these uncanny valleys now, things that were unimaginable to us 5 years ago. And now we can actually see what's it like to have a lifelike avatar and what's it like to have a chatbot that is indistinguishable from a human. And yeah, we transgress the uncanny valley, but we're also kind of like the fog of war is lifting. And this, the McCorduck effect, which is that a chorus of people say, well, that's not really intelligence, because once you actually see it, it doesn't seem like intelligence anymore. But we are feeling out the structure and space of what it is to be intelligent, which is quite interesting.
Yeah, definitely. I mean, I think we've just realized that the human brain is not very good at doing computation in the sense of like just thinking many steps ahead for chess or Go. I mean, we're very bad at dealing with this combinatorial explosion of moves. And I would say we're also to a certain extent bad at doing mathematics. Like that's maybe not what our genes enable us to do the best. On the other hand, we're excellent at pattern recognition, at thinking fast, using a very low amount of energy, and for example, recognizing faces. But these are all things that are enabled by core knowledge. I mean, we have all of these like dedicated systems for emotion recognition, face recognition, and so on that just enable us to operate as social animals in our community. And this has just evolved for a very long time. Throughout evolution. And I think, now that, playing Go is not a problem for machines and, playing StarCraft and whatever is not a problem, we're just realizing, okay, well, there are still these things that we can do much better than machines. And it seems like we're so good at this because we're so specialized at this. And the only way maybe to get that, at least like the most promising way to get it, in the next few years, is to reverse engineer core knowledge. I would say it's definitely not the only way to go, but it seems very promising.
Yeah, no, I agree, and I'm a huge fan of Tannenbaum, and yeah, I loved his Dream Coder paper. I've been trying
Yeah.
to get him on the podcast. He's a tough nut to crack, actually.
All right.
But yeah, no, I'm completely on board with that. And also, I mean, I think like the big elevator pitch for me is that all intelligence is specialized, and actually human intelligence is much more specialized and brittle than people think. I mean, I was thinking of a thought experiment last night. I mean, if you could have a perfect simulator of the world and us, and you placed yourself in this room, and then just like in the Matrix, you can just make the walls disappear, and now all of a sudden you realize you're in the ether and there's just white everywhere, and you're not in the real world anymore. And how quickly would mode collapse happen? Because you think you're so flexible, but you're now in this alien world, and all of a sudden, like, you just go crazy. Like all of these mental health problems materialize, and like basically full mode collapse. So we just assume that we are so flexible, we could live anywhere, we can do anything, and that's just not the case. Like we anthropomorphize everything and we delude ourselves, so that's the case.
That's true. That's true. And I would say, I mean, the 300 principle gives you a very nice perspective on this. It's like, as you get older, you get like more and more specialized at whatever it is you do. And I don't just mean work, but I mean like being at ease in your environment, in the environment that you surround yourself with. So you become like much more efficient, but you become much less adaptable.
Yeah.
And that's probably, and on the other hand, when you're like a little kid, you can probably adapt much better to these type of environments that you just mentioned that would be completely alien to us, because you're not so constrained by your posteriors, which have become very sharp. And adapted to a particular type of environment.
Yeah.
And I would say that's a weakness that we have as humans, like particularly in our age, in the sense that, there is this growing understanding that technological progress is exponential. I would say maybe a noisy exponential, and things are happening at a much, much faster pace. And then there is this quote that I absolutely love, is that, back in like 2 centuries ago, a problem for a person would be not being able to read and write. Now the equivalent in our century would be not being able to continuously learn, unlearn, and relearn. But what the 300 principle tells us is that once we get old enough, it becomes extremely hard to unlearn and extremely hard to relearn. And that's a weakness that we have that will make it possibly harder and harder to adapt to this growing pace of technological progress. And that's not a weakness that the machines that we will create have, because we have this thing called Bayesian model reduction of like pruning connections in the model of the world, in the generative model, where it becomes very easy for an agent to unlearn something to be able to relearn something.
Yeah, but I was thinking about that because we're talking about all of these priors, like the priors in the natural world, and I hadn't actually thought about that. That's a very interesting one. That agents tend to become more sclerotic. It's a bit like the simulated annealing algorithm.
Exactly.
Where at the beginning, ping pong balls going all over the place, and then over time, as the temperature decreases, it makes smaller and smaller.
Yeah, I love that.
And I'm not sure whether it would be, because you were kind of saying, well, it'd be a good idea not to have that prior in an agent. I'm not so sure. Having an exponential decay. Sorry, you do get that in like gradient optimization. So you have like weight decay over time. So like over time, the weight don't move. So it seems like a very natural thing to do. But there are so many examples of these priors that we just put into our models.
Yeah. Well, I think it's a great thing to have. But let's say you're like 80 years old and you move to a new country, you take on a new job. It's going to be very hard to adapt. When you have those very precise priors, it becomes a problem. Now, if you have a machine who's been in a warehouse for a very long time, and you put it in the outside world to interact with kids, you can just have it unlearn just by like modifying the code, and you will be able to relearn how to interact in this new environment in a very, very efficient way.
Yeah, I know. I was chatting about that earlier. I almost prefer the idea of killing an agent rather than kind of complexifying and adapting. But yeah, like there is a fine line. So one view is having like continual learning and adaptability, and another way is actually I'm just going to swap out the agent, so it effectively dies and just put a new one.
Yeah, that's actually probably an even faster solution. Yeah.
Anyway, I mean, so to sum up a little bit, I mean, there are 3 themes that we've been talking about. So first of all, like the agents, and then secondly, like structure learning and core knowledge. Just touching on the agents thing just for a second. I mean, I'm a huge fan of multi-agent, any kind of agent representation in general. And I guess, like, could you tease apart how much of the cache value is coming from the agent framework versus the active inference?
What do you mean by cache value?
Well, as in, like, there are many ways of implementing an agent framework. I mean, like, I could implement an agent framework, and I could solve like an Atari game, and I could like create a policy using, I don't know, like quality diversity or something like that. So, like, you get a lot just from having the agent framework. And what the agent framework allows you to do is there's an element of ensembling. So, like, being able to have like a population of different types of model that learn about the environment and like sort of dynamically sort of switching information between them. There's something quite magical about agents, even without the free energy principle.
Yeah, absolutely. Yeah, I mean, so the question is, what does really active inference bring to the picture in practice when we have agents interacting? Is that
So over and above, like, like multi-agent reinforcement learning or any other multi-agent system, like, what is the magic of applying FEP?
Yeah, I mean, that's a great question, and it's an even better question in the sense that most people in reinforcement learning are just wondering, why are we coming up with all of these things? And I would say, I mean, there's a few reasons. The first one is now we have a straight path from like first principles, math and physics to application. So there is some theoretical beauty to it, but then when it just comes to pragmatism, active inference, it brings you a lot of advantages in terms of safety and explainability. And I would say this is like a very big problem that, people are contending with deep learning and reinforcement learning overall. And that's...
Do you mean by virtue of the fact that having specialized agents is more intelligible, or do you mean by virtue of the fact that you can white box the predictive model?
I mean that the description of intelligence given by the free energy principle and active inference is extremely sparse and simple. It's just based on a generative model and minimizing free energy, which means that when the agent makes a particular decision, it becomes very simple to understand why it is that the agent did this particular thing. And so you can always trace it back to either the free energy minimization process or some representation of the world in the agent's generative model. So I think one of the biggest contributions of active inference practically is to unlocking safety and explainability. And so, for instance, I mean, we all want self-driving cars, right? And I would say I've been reading about self-driving cars for a very long time, and I've wanted it to happen, and it's just not happening because we have these systems who maybe take some particular decisions, and we're not able to trace back why they made this particular decision. Then it becomes too risky to, use RL to put in a self-driving car or do other things like assistive surgery. The stakes are just too high, and we place a lot of value in human life, and it's just not going to happen. With active inference, we're going to be able to get there eventually.
Could I push back on that a tiny bit, though? Because it sounds a little bit, like with a cellular automata, the underlying rules are very simple, but it gives rise to unimaginable complexity. So it sounds a little bit like you're saying, well, with the free energy principle, we understand, why it acted the way it did, but the predictive model that it represents is very, very complex. So we still don't understand it.
Yeah. So you could have the problem of like, you don't understand the generative model, but as we move forward, we're going towards more and more explainable generative models. So we had this conversation before of now we have like a synergy between mainstream machine learning and active inference, where we use components from machine learning, like we use deep learning neural nets, and we put them in the generative models to make them more expressive. I think that's a problem. I mean, it gets us somewhere for the time being, but it's a problem because as soon as you have neural nets and you put them in the generative models, you sacrifice explainability just because you don't understand what the neural nets are doing. As we move forward, the things that we're working on right now is to have generative models that have no neural nets. And we're not just the only group working on this. There's also at least, for example, the Tenenbaum group. I think Josh Tenenbaum, from the last conversation I had with him, he is really not keen on having neural networks do things, and he wants to move to generative models that are just very interpretable. And I would say there's two reasons for that. One of them is explainability. For all applications, this is really something we want to have. The other thing is for his particular agenda of understanding the human mind and cognition. If you want to, have an agent that reproduces the human cognition in some way, if you implement this agent in your neural networks, is not going to be able to tell you anything scientific.
I know, and this is something that I worry might be a really difficult thing to achieve.
Yeah.
Because we were talking about structural learning, so like maybe we could think of structural learning as a generative model, which, actually produces some intelligible structure about the current environment. But let's talk about Dreamcoder, which was Tenenbaum's paper. And he had this neural network that would essentially dream and learn to compose these primitive library modules that was in a different part of the system. And essentially you would get these programs which were compositions of like underlying functional primitives, and then they would be recursively recomposed, and then you run the model for several episodes, and these programs which are learned, even though they're comprised of primitives which are understandable, the overall composition of the program is now completely unintelligible. And I worry that with any form of structural learning, that will always be the case. Like, we'll never understand it.
Yeah, so I agree with you. But I would say we're pushing even further from that Dreamcoder paper. But just to step back a little bit, so from my latest conversations with Josh Tenenbaum, so he's of course very excited by this Dreamcoder work, and of course I can't speak for him, but the impression that I had is that he's more excited about doing structured learning with basically you would have like a set of building blocks, like basic building blocks, like primitives, and then you would do Bayesian inference to do structured learning. So you would infer based on those building blocks and basically the space of all models that you could have from those basic building blocks. Then you do Bayesian inference to solve that search problem and infer the right model to explain the world around you. Mm-hmm. Now, it all comes down to the building blocks that you're using. So you mentioned probabilistic programs. This is like a very interesting avenue of research, and this is definitely something that's pursued in the Tenenbaum lab. The problem, I guess, with probabilistic programs, as you mentioned, is that they can get unwieldy very quickly. I mean, if you just have a bunch of for loops and while loops and, do just a bunch of things, you could practically do anything. So it's very expressive, but it becomes very complicated and very hard to understand what the agent is doing. Yeah. What we're pushing forward in with Karl Friston and colleagues at Versus is the factor graph approach, where we will not have any deep neural networks, and we'll just have factor graphs that explain the world. Now, the factor graphs, they're amazing because each factor just corresponds to a representation of the world, and then the connections tells you, okay, this representation interacts with this, but more importantly, it doesn't interact with all of those other representations in the generative model. Yeah. So now you can see very efficiently what the representations of the agent are and how these connect with each other and how the flow of information in the agent's brain goes about. And so it becomes, I would say, as easy as it could get to understand why the agent did this particular thing. What was the agent thinking at this particular moment in time? What was the message passing between the agent's neurons and the agent's factors that led to this particular decision? At least, so this is what we're pushing towards. And I would say when you have that, then it becomes, it becomes as explainable as it could get.
Yeah, and I'm on board with that. So I think there are ways to structure, to add pressures to the structural learning process so that the priors which are selected mediate to things that we understand, and there were already pressures like parsimony, for example, which should be as simple as possible. But yeah, that makes a lot of sense. And the only reason I brought that up is, I've played around with Francois Chollet's ARC challenge, and he was big on the Spelke prize, and most of the solutions for that challenge were just kind of searching over a DSL of domain-specific operations on this 2D grid. And it's an exponential search, but when you look at the solutions, you just end up with this kind of brittle confection of programs, And then you kind of look at it and you're thinking, okay, well, weirdly it works quite well, but sure, it doesn't feel like it should work. And the winner of the ARC challenge actually said, I don't feel like a winner. I don't feel like what I've created here is any form of artificial intelligence.
Right.
And Minsky said, that we have a society of mind. We have many specialized programs for doing very different things, and that seems wrong. But again, at the right level of abstraction, when we talk about these priors, which should generalize in the environment we're in, it seems like the right thing to do. So it's just like finding the right
Yeah, for
position.
sure. Yeah. I also want to add, in terms of explainability, the free energy principle says that the best model to explain the world around you to do structured learning is the one that minimizes free energy. Free energy can be decomposed into accuracy minus complexity.
Mm-hmm.
So as you're optimizing free energy, you're getting sparser and least complex models. They need to be still very complex because they need to represent the world around us in an accurate way. But out of those models that do a good job of explaining the world around us, we're going to select the least complex ones. So we're going to prune as many connections in the factor graph as we can, which makes it more and more, easier to understand what the agent is doing.
I know, and it's a really interesting thing, because on the one hand, it's very principled just to have this underlying free energy principle, and the energy and the entropy, but then when you link it to things like the construction of factor graphs, you're almost kind of cajoling something which knows about energy and entropy, and as a byproduct, you might want it to produce a certain type of factor graph, or if it's an agent, you might want it to maintain a certain amount of behavioral complexity, or it needs to maintain these behaviors but have flexibility in these behaviors, and you might do that by indirect, like prodding the boundary, or kind of like doing weird things to it.
Well, yeah, maybe you would have to do that, but I feel, the best model is always going to be in relation to the data that the agent has gathered. So in principle, just by minimizing free energy, you would converge onto the right model.
Yeah.
But then I think the question also comes down to what is the model space that you're exploring, that you're allowing the agent to explore. And it then comes down to the types of primitives that you're using. And there's different schools of thought, right? There's the factor graph approach, there's the Tenenbaum approach, and probabilistic programs. One thing that really excites me from the Tenenbaum work is that they've converged to very similar models to the active inference community, but from a very, very different approach. So we have this principled take on active inference from the free energy principle and math and physics, which I would say is a top-down approach to artificial intelligence. This Tenenbaum crowd and colleagues, they've converged to very similar models from a bottom-up approach of doing a lot of experimentation with humans and fitting models. And they've converged to the expected free energy, expected utility and expected information gain as an objective to make informed and useful decisions. Mm-hmm. And they have all of these things that are just very close to what we're doing. And one paper that really excites me from the work that they did is on theory-based reinforcement learning, where they had this agent, which is basically an active inference agent, although they don't call it that way, interact in an Atari-like environment and do structured learning and interact with the environment using basically expected free energy. And what they do is they compare the learning trajectories of the agents with human participants playing the game for the first time. And they noticed that their agents had the same learning efficiency, the same sample efficiency as the humans. So they would learn the games in the same amount of time steps. But not only that, they had very similar learning trajectories, which is very exciting because to me, it's a proof of concept that active inference-like technology just reproduces the type of learning trajectories and the type of interacting with the world and learning about the world that we as humans do when we first interact with a new environment.
Yeah.
This is amazing.
That's fascinating. And only because I remember the DQN paper had millions of episodes until it converged.
Right.
And even then, it I don't think it was. Well, it was superhuman performance on many of the games. But yeah, okay, so you're saying not only does it, the sample efficiency is similar to humans, the conversion pattern is similar. And that's presumably testament to the fact that through this introspective awareness and knowledge of our priors and imbuing those into the system, it takes a similar trajectory as we would.
So actually, actually, I was surprised. For that paper, they did not have any core knowledge. Then they had a subsequent paper called Inductive Biases for Theory-Based Reinforcement Learning, where they added core knowledge, and then the agent was even better. Like it matched humans even more closely. But even without the core knowledge, it did a very good job. Now, the reason for that is that the environment that they took, it's not actually Atari, it's a simplified Atari with much less complexity. So you could argue that you don't really need core knowledge to solve that kind of task with human-like efficiency. But if you have core knowledge, then of course you're faster and you're better and so on. I would say as we move to more and more complex environments, core knowledge would probably play a bigger role insofar as we want human-like learning efficiency.
Yeah.
And of course that really depends on the goal of what we want, as we talked about just before.
Yeah. Lance, this has been absolutely amazing.
It's been great. Thank you so much.
Thank you so much. I've really enjoyed talking with you, and
Me too.
You gave a brilliant account of yourself. So thank you so much.
Thank you so much.
Cool.
Yeah, I love it.